Hello everyone, good evening. Today I will present our third project which was on tunnel design at downtown Dallas, Texas. Me and my groupmate Rahul CIV, we did this project under the supervision of Dr. Sadiq Khan. So let's get started. At first, I will talk about a little bit background of the project. This was a 25 feet tunnel which is going through the downtown Dallas as presented in the figure you can see, and a 10-story building was going to build. It was not actually going to build, it is actually existing there. So that 10-story building is here, and there is another building which is 15-story, and the tunnel is owned and regulated by Dallas Area Rapid Transit. The thickness of the lining of the tunnel is 24-inch. Now the thing is, there is another proposed building which is 20 storied, and the proposed building will have two basements in you like 20 feet under the ground. So now we have to see in the plexus model that how much deformation the tunnel faces because of the proposed building. Like if it's within the 10% limit, then we can say that they can build this building. So this was all about the background of the project. Now I will talk about a little bit objective. First, we will have to build a 2D FEM model using Plexis. Then we have to conduct the design documentation for the foundation and retaining system for the proposed 20-story building. Then we have to conduct the analysis in Plexis 2D with a feasible solution. Then we need to show the distress like deformation, shear stress, and lateral stress of the tunnel before and after the construction of the proposed building. So at first, I will talk about a little bit of model development. Obviously, in Plaxis, the first step of model development is creating the soil geometry. So at first, we will create the soil geometry. Then comes assigning the soil parameters from the given value. So the given soil parameters we used for the assigning material properties step. Then what we did, we create different phases depending of the activation of structures. Like at first we activated the loads, then we excavated the tunnel. So I will go into that later. Here is all the phases like initial phase, activate tunnel, excavation tunnel, diaphragm wall, first two phases of excavation, then activating bracing, then second two phases of excavation, then activating bracing 2, then we did dewatering, and then the new building was built there. Now after creating the phases, we simulated the model for each phase, and then from the simulation results we extracted the distress information, the deformation, the flexural stress, and we made comparison for two phases before and after construction of the proposed building and the new building. So that's solid, and in the end of the presentation we concluded some discussion. Now I will talk about creating the soil geometry. So this, the blue portion is soil 1, which was medium clay given, and the green portion is dense sand. And it was told in the project that the groundwater level will be 15 feet below. So this is actually full structure of the model that we developed. Here is one building that is 10 storied, and there is the another 15 storied building, and these were already there. So for one story it is 250 SF. So we just calculated it for the 10-story building. So and here you can see that there is the structure in the proposed structure, and for that we excavated the soil because it will be a 20 feet basement. It will have a 20 feet basement, and this is the tunnel. Now I will talk about the soil properties. So in case of the soil properties, you can see that we were given the soil information like the cohesion value, the friction angle, the moist unit weight, and also we were given the saturated unit weight. So from this we just put the values in the model like the C value, the phi value, and the unit weights value. And this is for the dense sand parameters. Now I will talk about the calculation results, the deform mesh for different phases. In the first phase, the initial phase, nothing was activated. Then you can see that I activated the load and activated the tunnel and made the excavation. Because of the tunnel activation and the load activation, the both side soils are a little bit downwards. And to remove these, we just gave the to diaphragm wall so that the downward soil can be pushed upward. And because of that, you can see that some of the soil is going in this side, because we just pushed two diaphragm wall inside of the soil. And then in the another phase, we started the excavation because we need to excavate 20 feet, but we can't do the excavation altogether. So at first we did 5 feet excavation, and for that you see that the soil is going a little bit upward for the unloading. And then we did the second excavation, and you can see that the soil is going a bit upward again. The soil height is less actually at this moment, so this height is actually showing that it's going upward. Then what we did, we activated the bracing so that the we can put the soil downwards again. And then this is the first bracing that we activated. And after activating the bracing, we did the third excavation, the third 5th feet. So um, we did the excavation in each step 5 feet. And then you can see that we did the another excavation, the last excavation actually. And here you can see a load. This is the load of the water, because after 15 feet there is water here, the groundwater level. So this load you are seeing, this is for the groundwater. And we are doing it 5 feet in each excavation. So this is our third excavation. And here you can see that we have activated the second bracing here to make the structure more stable. And then we did the dewatering because we have groundwater level here, so we had to do some dewatering. And then we did gave the load, the final load for the proposed building. And now you can see that the structure is a bit stable from the beginning. So that's how we created the geometry of the model. And now my partner Rahul Biswas will talk about how the displacement happened and what are the results and discussions are. So thank you very much.
Hello, good evening, everyone. Good evening, Dr. Khan. Now I'm going to discuss about the total displacement for the different phases that we created of our tunnel project. Uh, my group mate Anika already discussed how we create the soil properties, soil geometry, and uh, the different phases, as well as the deformed mesh of different phases. So now I'm going to tell you about the total displacement that occurred after the excavation or after the uh, adding new building load to our project. So here is a small video. So at first this picture shows the initial deformation condition with the existing building. The tunnel is not cut yet. So when the tunnel cut is made, we can see the highest amount of soil displacement occurred under the building which have the greater load. So the color code is showing red here. And later on, now we inserted our diaphragm wall uh, on the soil to resist the lateral earth pressure that from the existing building. Uh, Here is the displacement after the first cut we made of our excavation. We had to cut 20 feet depth in this analysis for to build two basement two basement for our new building. So at first we made the excavation layer by layer. So we choose to make the excavation at 5 feet depth. So this is the first 10 feet cut result is showing, and the intensity of the soil displacement is higher on the top of the tunnel. So now we can see we added two bracings anchored plate with our diaphragm wall to give our diaphragm wall a little bit extra support to resist the lateral earth pressure. Now the another 5 feet layer depth excavation is made. Now we can see the when we excavate our soil below the groundwater table. Our groundwater table is at 15 feet. So after the cut we made at 20 feet, we can see there are water pressure uniform acting downward as uniform load. Still, the highest amount of soil displacement occurs at the top of the tunnel. So now our second layer bracing is applied to give our diaphragm wall more extra support to resist against the lateral earth pressure. And here is the dewatering phase. We then before construction we dewatered the water from our excavation site. So there is a little bit of drop down of the groundwater table. And now we created a new building which is 20-story building including two basement, that is we considered as 22-story building. Per floor area has a load of 250 psf, pound per square feet. So after the construction we can see the amount of soil displacement uh, that occurred over the tunnel. So here is the comparison of two of axial forces of the tunnel before and after the construction. Uh, the first picture is showing the axial forces that acting on our tunnel reinforced concrete at the existing condition, uh, and the right side picture is showing the axial force that is acting on our tunnel reinforced concrete after the new building construction. So as from the value we can see the axial forces increased very significantly. The maximum value was before was 40.46 pound feet per feet, which becomes 56.12. And same as here is a shear force comparison for our tunnel before construction and the after construction. Shear force value is also increased significantly in this case. The next slide is about the bending moment on the tunnel concrete. The bending moment intensity, you can see the intensity of bending moment increased very rapidly. The maximum in both cases, the positive bending moment and negative bending moment both actually increased. So the maximum value of positive bending moment before construction was 1.989 into 10 to the 6, which is pound feet per feet strip, and that maximum value becomes after the construction it becomes 2.769. So we can see a significantly increasing axial shear force and bending moment changes on the tunnel concrete with the construction of new building. So here is a graph that is showing the bending moment changes, the maximum positive moment and the maximum negative moment changes for existing condition and as well as for proposed new building condition. So you can see the maximum positive bending moment increased more than the maximum negative bending moment if we compare the both maximum positive bending moment and the negative bending moment. And as also it's a comparison of flexural stress. For calculating flexural stress we actually use the formula of mc divided by I, where m is the bending moment and we take the moment of inertia for per feet strip of our tunnel concrete. So from that equation, we can see changes in percentage. That is the positive moment increase 39.22%. If we compare it with the negative moment, the flexure stress also increases like 23.09% before construction and the after construction. Before the that means in existing condition, the amount of flexure stress was there. It increases like 39 or 23 times, 39% or 23%, if we compare it. So this is an observation. And last of all, the project was about a tunnel that went under the downtown Dallas area. A 25 5 feet tunnel diameter was given. Texas Dallas area rapid transit actually allows construction over the tunnel only if it causes on 10% distress in axial shear force and flexural stress. But here, after the analysis of Plaxis, we can see the amount of changes in shear and axial forces as well as the flexural stress is much more than the 10%. We also see a 38% increment in the axial force of the tunnel before and after construction. From the analysis, we saw that the soil displacement also happened over the tunnel if the Dallas rapid transit area, if the Dallas authority actually give the permission to construct a new building over the tunnel. So from the analysis, it is not our recommendation for the Dallas area rapid transit uh, to give the permission to build a new building over the tunnel. So as the changes in deformation in axial shear force and flexure stress more than 10%, we actually do not recommend to give the permission to build a new building over the tunnel. So that's all from our group. Thank you so much, everyone, for your time.